What if you could step through a doorway and emerge in another galaxy? Picture a tunnel carved into the fabric of space and time, a shortcut so profound it defies everything we know about distance and speed. This isn't science fiction, it's the tantalizing promise of wormholes, one of the most mind-bending concepts in theoretical physics. For decades, scientists have wrestled with the idea that these cosmic gateways could exist, bending the rules of the universe as we understand them. And today, we're diving deep into 30 groundbreaking theories that could reshape how we think about space-time travel forever. Think about the sheer scale of the cosmos for a moment. Even the closest stars are so far away that reaching them within a human lifetime seems impossible with our current technology. But what if the universe has its own hidden pathways? Wormholes, if they exist, could be the ultimate loophole bridging unimaginable distances in the blink of an eye. Imagine standing at the threshold of one, peering into a tunnel that warps space itself, connecting two points that should be eternally apart. The implications are staggering: interstellar travel, time dilation, even the possibility of parallel universes. It's enough to make your head spin, and that's just the beginning. This isn't just about wild speculation, though. Behind every theory lies the rigorous work of physicists pushing the boundaries of human knowledge. From Einstein's equations hinting at these cosmic shortcuts to modern researchers exploring the stability of wormholes with exotic matter, the science is as thrilling as it is complex. And that's why we're here, to unravel these ideas piece by piece, demystifying the extraordinary without losing the wonder. Over the next 30 theories, we'll explore everything from black hole connections to the mind-bending idea of traversable wormholes. So buckle up, because by the end of this journey, you'll never look at the night sky the same way again. Einstein and his colleague Nathan Rosen first cracked open the door to this cosmic possibility back in 1935. While working through the complex equations of general relativity, they stumbled upon something extraordinary, a hidden feature of space-time that acted like a tunnel linking two distant regions. They called it a bridge, a term that feels almost humble compared to the grandeur of what it represents. Picture space as a vast sheet of fabric, warped and dimpled by stars and galaxies. Now imagine pinching two distant sections of that fabric together until they nearly touch, then piercing through to create a passage between them. That's the essence of an Einstein-Rosen bridge, a concept so radical it redefined how physicists think about the structure of the universe. The math behind this idea is rooted in Einstein's field equations, which describe how matter and energy curve space-time. Under the right conditions, those equations allow for shortcuts, regions where space folds in on itself, creating a throat-like passage between separate points. But here's the catch: these early wormholes were more like mirages than usable highways. The moment anything tried to pass through, whether matter or even light, the bridge would snap shut like a trapdoor. The forces at play were so extreme that the throat of the wormhole would collapse faster than anything could traverse it, leaving would-be travelers stranded. It's like building a bridge out of tissue paper. The structure exists, but it couldn't hold the weight of a single footstep. Yet the sheer existence of such a possibility sent shockwaves through the scientific community. Even if these bridges were unstable, their theoretical foundation was rock solid, proving that space-time could be manipulated in ways that defied classical physics. Think about what that means. The universe's rulebook might contain loopholes after all. For decades, physicists wrestled with this paradox. How could something so elegantly predicted by math be so fragile in reality? That tension between theory and practicality became the launching pad for countless later breakthroughs as researchers began asking the next big question: if nature abhors a wormhole, could we find a way to prop one open? For decades after Einstein and Rosen's discovery, wormholes remained little more than mathematical curiosities, beautiful in theory but useless in practice. That all changed in 1988 when physicists Michael Morris and Kip Thorne dared to ask a bold question. What would it take to make a wormhole you could actually travel through? Their answer rewrote the rules of the game. Imagine a tunnel through space-time that doesn't collapse the moment you step inside, one held open not by fragile equations, but by something even stranger, exotic matter. This hypothetical material defies everything we know about physics. Unlike ordinary matter, which gravitates toward other objects, exotic matter would possess negative energy density, effectively pushing space-time outward instead of pulling it inward. Picture trying to hold open a doorway by propping it up with repelling magnets, except here, the magnets are made of a substance that warps the very fabric of reality. Morris and Thorne calculated that lining a wormhole's throat with this bizarre material could counteract the crushing forces of gravity, creating a stable passageway. Suddenly, the impossible seemed within reach, but here's the catch: no one has ever found exotic matter in nature. The closest we've come is the Casimir effect, a quantum phenomenon where two uncharged metal plates, placed infinitesimally close in a vacuum, experience a slight pull due to fluctuations in quantum fields. It's a whisper of negative energy far too weak to hold open a cosmic gateway, but proof that the concept isn't entirely science fiction. The challenge: scaling this effect up to astronomical proportions would require technologies and energies beyond anything we can currently fathom. Even if we could somehow harvest or manufacture enough exotic matter, the engineering hurdles are staggering. A traversable wormhole would need to be absurdly large, thousands of kilometers wide, to prevent tidal forces from tearing travelers apart. And then there's the question of control. Opening a wormhole is one thing, choosing where and when it leads is another. Without precise manipulation, you might step through only to emerge in the heart of a star or a billion years in the past. The margin for error is non-existent, yet the Morris-Thorne model remains a cornerstone of wormhole physics because it proves that traversability isn't just a fantasy, it's a problem waiting to be solved. Their work sparked a new wave of research, from studying quantum vacuum energy to theorizing about advanced civilizations harnessing black holes. It's a reminder that the universe's greatest mysteries often begin with a simple shift in perspective. Instead of asking if wormholes could exist, we're now asking how. And that changes everything. John Wheeler's vision of space-time wasn't the smooth, unbroken fabric we often imagine. It was a seething, turbulent ocean. At the smallest scales imaginable, far smaller than an atom, he proposed that the universe bubbles with a chaotic froth he called quantum foam. Picture the surface of a boiling pot, but instead of water, it's the very structure of reality itself, constantly churning with tiny wormholes and tunnels that flicker in and out of existence in fractions of a second. These aren't the cosmic gateways of science fiction. They're quantum-scale fluctuations so brief and minuscule they're practically ghosts. Yet their existence hints at something profound, the hidden turbulence beneath the apparent calm of space. This idea emerges from the clash between Einstein's relativity and quantum mechanics. At the Planck scale, a distance so small it's a trillion times tinier than a proton gravity, and quantum forces battle for dominance. In this realm, space-time isn't stable. It's a storm of virtual particles, energy spikes, and fleeting distortions. Wheeler suggested that wormholes could be part of this chaotic dance, forming when the foam's bubbles momentarily connect before collapsing again. It's like watching microscopic bridges build and crumble in a cosmic blink, a reminder that even emptiness is alive with activity. But here's the tantalizing question: could these quantum wormholes ever be more than fleeting anomalies? Scaling them up to human traversable sizes would require energies and technologies beyond our wildest dreams. The energy needed to stabilize even a single proton-sized wormhole would dwarf the output of 1,000 stars. And yet, some theorists speculate that advanced civilizations, or future humans, might one day harness the foam's turbulence, coaxing these microscopic tunnels into something larger. Imagine stretching a soap bubble until it becomes a doorway. The principle is just as delicate, just as fraught with unknowns. The real significance of quantum foam lies in what it teaches us about gravity's quantum nature. If wormholes flicker in and out of existence at this scale, they might be the missing link in a theory of quantum gravity, a way to reconcile the colossal and the infinitesimal. Some models even suggest that particles could traverse these microscopic tunnels, appearing to teleport across space in ways that defy classical physics. It's a reminder that the universe's smallest quirks might hold the keys to its grandest mysteries. So while we're not stepping through quantum wormholes anytime soon, their existence whispers a thrilling possibility. The fabric of reality might be far more malleable and far stranger than we ever imagined. What if a wormhole could do more than bridge distant stars? What if it could bend time itself? The idea isn't as far-fetched as it sounds. According to Einstein's theory of relativity, time isn't a fixed river flowing at the same speed for everyone. It's more like a stretchy fabric warped by gravity and motion. If you could take one end of a wormhole and accelerate it to near light speed or park it near a black hole's crushing gravity, time would slow down for that end compared to the other. The result, a tunnel through space that's also a tunnel through time. Step in one side and you might emerge centuries or even millennia in the past or future. Think of it like this. Imagine two clocks placed at either end of a wormhole. One clock sits on Earth ticking away normally. The other is strapped to a spaceship racing at 99% the speed of light. Due to time dilation, the mind-bending effect where high speeds slow time, the ship's clock would fall far behind Earth's. Now, if you could step through the wormhole from the ship back to Earth, you'd effectively be traveling to Earth's past relative to the ship. It's not magic, it's physics pushed to its limits. The wormhole becomes a bridge not just between places, but between moments. But here's where things get messy. Stephen Hawking famously wrestled with the implications of time travel via wormholes, particularly the dreaded grandfather paradox. What if you went back in time and accidentally prevented your own birth? The universe, Hawking argued, seems to abhor such contradictions. He even proposed the chronology protection conjecture, a cosmic rule that might prevent time travel outright, as if nature itself slams the door on paradoxes. Wormholes, in this view, might snap shut the instant someone tries to misuse them as time machines, crushed by the weight of their own impossibility. Yet other physicists aren't so quick to dismiss the idea. Some suggest that quantum mechanics could offer loopholes. In the many worlds interpretation of quantum theory, every possible outcome spawns a new universe. So if you traveled back and altered the past, you wouldn't rewrite history. You'd simply branch off into a parallel timeline where your actions never create a paradox. It's a dizzying thought. Wormholes might not just connect points in space and time, but entire alternate realities. The debate rages on because the stakes are so high. If traversable wormholes exist, and if we could control them, humanity would gain not just the stars but the ages. But until we unravel the deepest mysteries of quantum gravity and exotic matter, these ideas remain tantalizingly out of reach. What's clear is this: wormholes don't just challenge our understanding of space, they force us to rethink the very nature of cause, effect, and the arrow of time itself. And that's a puzzle even Einstein might find thrilling. Black holes have long been the ultimate cosmic enigmas, regions of space where gravity is so intense that nothing, not even light, can escape their grip. But what if these monstrous voids aren't just in points? What if, hidden beneath their event horizons, some black holes disguise something far stranger, a wormhole, a tunnel to another place or time? This radical idea flips our understanding of black holes on its head, suggesting they might not be the dead ends we once thought, but gateways instead. The math behind this theory traces back to Einstein's equations, which allow for black holes to connect to white holes, theoretical regions where matter and energy can only exit, never enter. Together, they could form a bridge, a wormhole with the black hole as its entrance and the white hole as its exit. Picture a cosmic hourglass with matter funneling in one side and spraying out the other. But here's the catch: white holes are purely hypothetical, and no observational evidence has ever confirmed their existence. Without them, the wormhole hypothesis remains a tantalizing what if. Yet some physicists argue that even without white holes, black holes might still hide wormholes. The key lies in what replaces the singularity, the infinitely dense point at a black hole's heart. Instead of a crush of infinite density, there could be a throat leading elsewhere, like a hidden passage in a labyrinth. The challenge, crossing it, would mean surviving forces so extreme they'd shred atoms. Even if a wormhole lurked inside, reaching it might be impossible, a twist that turns the theory into a cosmic tease. This idea collides head-on with another puzzle, the firewall paradox. Quantum mechanics suggests that the event horizon of a black hole should be a seething wall of energy, incinerating anything that crosses it. But relativity insists it should feel like empty space to a falling observer. If black holes conceal wormholes, this paradox deepens. Does the firewall guard the entrance, or does the wormhole's geometry somehow neutralize it? The debate splits physicists, with some proposing that wormholes could resolve the paradox by redirecting the destructive energy elsewhere, like a cosmic pressure valve. Then there's the holographic principle, which suggests that all the information swallowed by a black hole isn't lost but encoded on its surface. If a wormhole hides inside, this information might not be destroyed, just transferred. Imagine a black hole's accretion disk, that glowing ring of superheated gas spiraling inward. According to this view, the disk isn't just a death spiral, it's a data storage device, its flickering light holding the blueprint of everything that falls in. The wormhole, then, could be the universe's way of preserving that information, funneling it to another location or time. Visualizing this isn't easy, but think of it like a black hole's shadow theater. From the outside, we see only the two-dimensional play of light and matter on the event horizon. The wormhole, if it exists, is the hidden machinery behind the curtain, shaping the performance. Observations of black holes like M87 star, the first ever imaged hint at complexities beneath their inky surfaces. Strange distortions in their accretion disks or unexpected energy flares might one day betray the presence of something more than a singularity. Of course, skepticism abounds. Without direct evidence, the black hole-wormhole connection remains speculative, a thrilling could be rather than a proven is. Yet that's the beauty of theoretical physics. It pushes us to imagine the universe not as it seems, but as it might be. Whether black holes are cosmic trash compactors or secret passageways, the quest to understand them forces us to confront the limits of space, time, and reality itself. And that's a journey far too fascinating to resist. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their path, white holes would be their polar opposites, cosmic fire hydrants blasting matter and energy outward with unstoppable force. These hypothetical objects emerge straight from Einstein's equations as the time-reversed twins of black holes. While a black hole's event horizon marks a point of no return, a white hole's boundary would be a point of no entry. Nothing gets in, but anything inside gets expelled violently, like a cosmic reset button firing everything back into the universe. The symmetry between the two is mathematically elegant. Run the equations for a black hole backward in time, and you get a white hole. Where a black hole traps light, a white hole repels it. Where a black hole's gravity warps space inward, a white hole's would warp it outward. Some theorists suggest this duality could solve one of wormhole theory's biggest puzzles, the exit problem. If a traversable wormhole needs two ends, a black hole might serve as the entrance while a white hole acts as the exit. a one-way tunnel stitching together distant corners of space-time. But here's where the theory hits a snag. White holes violate the second law of thermodynamics, which states that entropy or disorder always increases. A white hole spontaneously spewing out ordered matter and energy would essentially reverse this flow, like a shattered glass reassembling itself midair. That's why many physicists argue white holes can't exist in our universe, or if they did, they'd be incredibly short-lived, collapsing instantly under the weight of their own impossibility. So why keep theorizing about them? Because the universe has a habit of surprising us. Take gamma-ray bursts, for example, some of the most energetic explosions ever observed. For decades, their origins were a mystery. Could a handful of these extreme events actually be the death throes of white holes? It's a long shot, but if true, the implications would be staggering. A white hole's outburst would carry a unique signature, an absence of incoming material paired with an abrupt, directional surge of energy. Telescopes haven't spotted anything matching that description yet, but the search continues. There's another twist. Some models suggest white holes might not be standalone objects at all, but rather black holes experiencing a delayed cosmic rebirth. In loop quantum gravity, a theory attempting to reconcile relativity with quantum mechanics, a collapsing black hole could rebound into a white hole once it reaches maximum density. Picture a star collapsing into a black hole, then after a pause that could last billions of years, exploding back outward as a white hole. It's as if the universe hit the undo button, transforming a cosmic dead end into a new beginning. The catch: observing this would require patience on timescales dwarfing human history. And even if white holes exist, they might not resemble the pristine exits wormhole travelers would hope for. The energy blasting outward could resemble a particle accelerator gone haywire, turning any exit attempt into a lethal plunge through a storm of radiation. Yet the very possibility keeps physicists probing. If white holes are real, they'd rewrite our understanding of cosmic evolution, offering a glimpse into how the universe might recycle space-time itself. Until then, they remain one of the most tantalizing what-ifs in theoretical physics, a reminder that even the wildest ideas can reshape our view of reality. What if the key to unifying Einstein's general relativity with the bizarre world of quantum mechanics has been hiding in plain sight, woven into the very fabric of space-time itself? That's the bold claim behind the ER=EPR conjecture, a revolutionary idea that ties wormholes directly to one of quantum physics' strangest phenomena, entanglement. Proposed by physicists Juan Maldacena and Leonard Susskind, this theory suggests that wormholes' Einstein-Rosen bridges aren't just cosmic shortcuts, but physical manifestations of quantum entanglement. It's a connection so profound it could bridge the two greatest pillars of modern physics. To grasp how radical this idea is, think of entanglement first. When two particles become entangled, their properties sync instantaneously, no matter how far apart they are. Measure one's spin as up, and the other instantly becomes down, even if separated by the width of a galaxy. Einstein famously called this spooky action at a distance because it defies classical notions of locality and speed. Now, imagine that this eerie link isn't just a mathematical quirk, but a tiny, stretched-out wormhole threading through space-time, invisibly binding the particles. That's the heart of ER=EPR. Entanglement and wormholes might be two sides of the same cosmic coin. The implications are staggering. For decades, physicists have struggled to reconcile relativity, which governs the vast, smooth curvature of space-time, with quantum mechanics, which rules the chaotic, probabilistic realm of the ultra-small. Wormholes, in this view, could be the missing stitch that sews the two together. Picture space-time not as a static stage, but as a dynamic tapestry where every entangled pair of particles is connected by microscopic threads, weaving a hidden network of quantum tunnels. At scales too small to measure, the universe might be teeming with these ephemeral wormholes, popping in and out of existence like bubbles in a quantum foam. But how could something as tangible as a wormhole emerge from something as abstract as entanglement? Maldacena and Suskind's math suggests that the geometry of space-time itself might encode quantum information. In their framework, a wormhole's throat isn't just empty space, it's a physical manifestation of the entangled states shared between distant particles. It's as if the universe, when faced with the paradox of spooky action, simply folds space to make the connection literal. This wouldn't just explain entanglement, it would ground it in the fabric of reality, turning an abstract link into a geometric one. Critics, of course, raise tough questions. If every entangled pair is secretly joined by a wormhole, why don't we see their gravitational effects? The answer might lie in scale. These hypothetical wormholes would be vanishingly small, perhaps existing only at the Planck length, a scale so tiny it's a billionth of a trillionth the size of a proton. Probing such distances is beyond any technology we can imagine today, but supporters argue that the math holds up, and if it's right, it could reshape everything from black hole physics to quantum computing. The boldest takeaway: if ER equals EPR is correct, then building a quantum computer might inadvertently mean constructing a network of microscopic wormholes. Every time we entangle qubits in a lab, we could be knitting together tiny bridges in space-time without even realizing it. It's a dizzying thought. The same phenomenon that powers cutting-edge technology might also hold the blueprint for the universe's deepest architecture. Yet for all its elegance, the theory remains unproven. No experiment has yet bridged the gap between quantum entanglement and wormhole geometry. But that's the thrill of theoretical physics. The best ideas don't just answer questions, they redefine what questions are worth asking. Whether ER equals EPR holds up or not, it's already done something remarkable. Turn the cosmos into a puzzle where gravity, quantum weirdness, and the shape of reality itself might all fit together. And that's a breakthrough worth dreaming about. String theory rewrites the rules of the universe by proposing that space isn't just three-dimensional, it's a symphony of hidden dimensions, curled into shapes so tiny we've never detected them. These extra dimensions could hold the secret to stable wormholes, not as fragile anomalies, but as fundamental features of reality. Picture space as a loaf of bread, where our familiar three dimensions are just the crust. Inside, countless microscopic folds called Calabi-Yau manifolds twist through 6 additional dimensions, their intricate geometry dictating how particles and forces behave. If these hidden folds contain bridges or tunnels, wormholes could exist as naturally as atoms, woven into the fabric of the cosmos itself. The magic lies in how string theory reimagines gravity. In our everyday world, gravity is the weakest force, but in higher dimensions it might gain strength, leaking through these hidden geometries like water seeping through cracks. A wormhole in this framework wouldn't need exotic matter to stay open. The extra dimensions could stabilize it inherently, like the vaulted arches of a cathedral distributing weight to prevent collapse. Some models even suggest that the throat of a wormhole could be a filament of higher dimensional space, a cosmic string, under unimaginable tension, acting as a scaffold to keep the tunnel intact. Then there's the brain-world scenario, another radical idea from string theory. Imagine our universe as a 4-dimensional membrane, or brain, floating in a higher dimensional bulk. Other brains might hover nearby, separated by cosmic distances in dimensions we can't perceive. Wormholes in this context could be shortcuts piercing through the bulk, connecting our brain to another like threads stitching through layers of fabric. Travel through one, and you're not just crossing space, you're hopping between realities. The implications are staggering. A wormhole might not just link 2 points in our universe, but bridge entirely separate brain worlds, each with its own physics and history. Visualizing this isn't easy, but think of a folded sheet of paper with ants crawling on its surface. To the ants, the distance from one side to the other seems vast. But poke a pencil through the fold, and suddenly there's a shortcut, a wormhole through the third dimension the ants never knew existed. Now imagine that pencil isn't just piercing through empty space, but through a labyrinth of curled-up dimensions and vibrating strings. That's the scale of complexity string theory brings to the table. Critics argue that without experimental proof, these ideas remain elegant speculation. The energy scales required to probe extra dimensions are trillions of times beyond what our particle colliders can achieve. But supporters counter that wormholes might leave subtle fingerprints, like gravitational waves with anomalous frequencies or particles that appear to tunnel through unseen dimensions. Future telescopes or quantum gravity experiments could one day spot these clues, turning mathematical poetry into observable reality. What's undeniable is how string theory stretches our imagination. By invoking extra dimensions, it transforms wormholes from precarious cosmic flukes into inevitable features of a richer, more layered universe. Whether they're threads through Calabi-Yau manifolds or bridges between brains, the message is clear. The key to traversable wormholes might not lie in overcoming physics as we know it, but in uncovering the physics we've yet to see. The idea of negative energy sounds like something ripped straight from a sci-fi novel. A substance that repels rather than attracts, bending space-time in ways ordinary matter never could. Yet this bizarre concept isn't just theoretical. It might be the linchpin holding wormholes open against the universe's relentless urge to crush them shut. Picture a tunnel carved into the fabric of reality, its walls lined with a material that pushes outward against gravity's relentless pull, like a cosmic airlock fighting to stay open. That's the promise of exotic matter, a hypothetical substance with negative energy density, and without it, traversable wormholes would collapse faster than a house of cards in a hurricane. The math behind this is as elegant as it is strange. Einstein's equations show that stabilizing a wormhole requires something to counteract the immense gravitational forces pinching its throat closed. Enter exotic matter, which would defy the fundamental rules we associate with normal particles. While everything in our everyday experience, planets, stars, even light, obeys the so-called null energy condition, exotic matter flips the script. It's like discovering a type of glue that doesn't just bind things together, but actively repels them, creating tension where there should only be collapse. The closest we've come to glimpsing this phenomenon is the Casimir effect, a quantum quirk where two uncharged metal plates placed nanometers apart in a vacuum experience a faint pull. Why? Because the space between them excludes certain quantum fluctuations present outside, creating a subtle imbalance, a whisper of negative energy. It's not enough to prop open a wormhole, of course. Scaling this up to cosmic proportions would require harnessing energies comparable to entire stars, and that's assuming the effect could even be amplified that far. This raises the billion-dollar question: could exotic matter exist naturally in the universe, hidden in the depths of space? Some theorists speculate that certain quantum fields, stretched to extremes near black holes or in the early universe, might have produced pockets of negative energy. Others point to dark energy, the mysterious force accelerating the universe's expansion, wondering if it shares properties with the exotic matter needed for wormholes. But here's the catch: even if such material exists, collecting enough of it to stabilize a macroscopic wormhole would be like trying to gather fog in a sieve. Then there's the engineering challenge. Suppose we could synthesize exotic matter in a lab. The amounts required would be astronomical, literally. Calculations suggest that to keep a wormhole just 1 meter wide open for a single second, you'd need a chunk of exotic matter with the mass energy equivalent of Jupiter. And that's before factoring in the precision needed to line the wormhole's throat perfectly, ensuring it doesn't destabilize and implode mid-transit. One irregularity and the tunnel becomes a death trap. Yet for all the obstacles, the very possibility ignites imaginations. Advanced civilizations, if they exist, might have cracked the code, tapping into quantum fields or manipulating space-time at levels we can't yet fathom. Or perhaps exotic matter isn't a substance to be found or made, but a feature of space-time itself, waiting to be unlocked through deeper understanding. The debate isn't just about wormholes, it's about probing the outer limits of physical law, testing whether the universe permits shortcuts or if it insists on keeping its doors locked. What makes this theory so compelling isn't just the how, but the why. Negative energy challenges our most basic assumptions about reality, suggesting that the universe's rulebook has pages we haven't even glimpsed yet. Whether exotic matter remains a tantalizing what if or becomes the key to the stars, its study pushes physics into uncharted territory, where the line between impossibility and breakthrough is as thin as the fabric of space-time itself. And that's a frontier worth exploring. Imagine the universe in its infancy, a seething cauldron of energy, cooling and stretching in the first moments after the Big Bang. In that primordial chaos, tiny imperfections might have formed in the fabric of spacetime itself, like cracks in hardening glass. These defects, known as cosmic strings, aren't your ordinary celestial objects. They're theoretical one-dimensional scars, thinner than a proton but stretching across billions of light years, with densities so immense a single inch could weigh more than Mount Everest. And if they exist, they might be the ultimate cosmic sculptors, carving wormholes into the very structure of reality. The idea hinges on spacetime's elasticity. When the early universe underwent phase transitions akin to water freezing into ice, its fundamental fields might have gotten stuck in misaligned configurations, leaving behind these bizarre strings as topological relics. Picture pulling apart a piece of taffy until it forms thin, ragged strands, except here, the taffy is space-time and the strands are cosmic strings, vibrating with enough gravitational energy to warp everything around them. Now, if two such strings were to cross or twist in just the right way, their immense tension could pinch space-time so severely that it folds inward, forming a tunnel. A wormhole created not by exotic matter, but by the raw geometry of the universe's birth pangs. Detecting these strings, let alone their wormhole offspring, is no easy feat. Unlike black holes, they don't emit light or swallow stars, but their gravitational influence could betray them. A cosmic string drifting through space would create a telltale double image effect, where light from distant galaxies bends around it like a prism, producing identical copies of the same star or quasar. Some astronomers have even scoured sky surveys for these ghostly duplicates, though none have been definitively found. Another clue might lie in gravitational waves. A snapping cosmic string could send ripples through spacetime with a unique frequency signature, like a plucked guitar string ringing across the cosmos. The real challenge is proving that these strings could spawn wormholes. The math suggests it's possible, but the conditions would have to be exquisitely precise. The strings would need to be moving at nearly light speed when they intersect, their gravitational fields twisting spacetime like braided ropes. Even then, the resulting wormhole might be microscopic, or worse, unstable, collapsing before anything could traverse it. But if just one survived, the implications would be staggering. A network of string-borne wormholes could weave through the universe like hidden subway lines, connecting distant epochs or even parallel dimensions. Critics argue that cosmic strings are a long shot, a relic of theories that might not match our actual universe. Yet the hunt continues, because if they're out there, they'd be more than just cosmic oddities. They'd be living fossils from the universe's first moments, and possibly the architects of its greatest shortcuts. Whether they're the key to wormholes or just another tantalizing dead end, their study forces us to confront a profound truth. The universe's wildest possibilities often lie hidden in its oldest scars. And that's a mystery worth unraveling. The dream of building a wormhole isn't just for physicists, it's the stuff of engineers' wildest ambitions. Picture a civilization advanced enough to stitch the fabric of space-time itself, crafting tunnels between stars like cosmic road builders laying interstellar highways. But how forget exotic matter scooped from black holes or relics from the Big Bang? The real breakthrough might lie in manipulating the universe's most elusive forces. Dark energy, that mysterious agent accelerating the expansion of the cosmos, could be the ultimate construction material. If we could somehow bottle its repulsive effect, we might have the perfect counterbalance to gravity's crushing grip, lining a wormhole's throat with a force that pushes space outward instead of letting it collapse. The challenge, of course, is that dark energy doesn't exactly come with an instruction manual. We've detected its influence, galaxies flying apart faster than they should, but we still don't know what it is. Hypothetical technologies might one day mimic its effects using engineered quantum fields, creating localized bubbles of negative pressure. Think of it as cosmic 3D printing, where we don't just build structures in space, but of space itself. The energy requirements would be astronomical, perhaps requiring the collective output of a Dyson sphere harnessing an entire star's power. But if you're going to rearrange the universe's geometry, you'd better bring a universe-sized toolkit. Then there's the quantum vacuum, a seething ocean of virtual particles popping in and out of existence. Under the right conditions, these fleeting fluctuations might be coaxed into alignment, their combined energy stabilizing a wormhole's fragile structure. It's like trying to build a bridge out of soap bubbles, except each bubble is a fragment of spacetime twisted into coherence by precision physics. Some models suggest that ultra-advanced nanotech could orchestrate this chaos, deploying swarms of quantum-scale machines to tune the vacuum like a symphony conductor shaping sound. The result, a self-reinforcing wormhole held open not by brute force, but by the delicate interplay of particle and void. Sci-fi staples like stargates gloss over the gritty details, but reality would demand solutions far beyond spinning rings or glowing portals. Even if we cracked the stabilization problem, there's the matter of targeting. Opening a wormhole is one thing, aiming it is another. The exit point couldn't just be somewhere in the Andromeda galaxy. It would need to avoid stars, planets, and any other gravitational hazards that might destabilize the tunnel. Navigation might require a network of quantum-entangled beacons, their instantaneous communication providing real-time updates to steer the wormhole's far end with pinpoint precision. And let's not forget the human factor. Traversing a wormhole isn't like boarding a spaceship. Tidal forces near the throat could stretch atoms like taffy unless the tunnel's curvature is flawlessly smooth. Radiation shielding would need to handle energies that make supernova look tame. Then there's the psychological toll. Stepping through a portal where the laws of physics twist like a funhouse mirror might be more than any unaided mind could handle. Future engineers might need to design not just the wormhole, but the travelers themselves, augmenting biology or even transferring consciousness into hardened synthetic forms. This isn't just about bending the rules of physics, it's about rewriting them. The technologies required are dark energy manipulation, vacuum engineering, quantum AI sound like magic today. But so would smartphones to a medieval peasant. The lesson isn't that wormholes are impossible, it's that they demand a paradigm shift in how we harness the universe's deepest mechanisms. Until then, they remain the ultimate engineering challenge. A project that doesn't just cross continents or oceans, but the vast, star-studded gulf between impossibility and inevitability. Could dark matter, the invisible substance making up most of the universe's mass, hold the key to unlocking wormholes? It's a radical idea, but some physicists suspect these two cosmic mysteries might be intertwined in ways we're only beginning to grasp. Picture this: streams of dark matter particles, normally drifting unseen through space, might be funneled through microscopic wormholes like water through hidden underground channels. If true, it would mean these elusive particles aren't just passive bystanders, they could be actively shaping the fabric of spacetime itself. The logic starts with dark matter's gravitational grip. We know it outweighs visible matter 5-to-1, bending light and sculpting galaxies with its invisible pull. But what if its influence goes deeper? Certain models suggest that dense concentrations of dark matter could warp spacetime enough to create fleeting wormholes, especially in regions like galactic cores or the hearts of dark matter halos. Think of it like a heavy ball resting on a trampoline. The weight of dark matter might dent spacetime so severely that adjacent points pinch together, forming temporary bridges. These wouldn't be the stable, human-sized tunnels of sci-fi, but subatomic gateways flickering in and out of existence, perhaps even serving as conduits for dark matter itself. Here's where things get even stranger. Some theorists propose that dark matter particles, often assumed to be weakly interacting massive particles, or WIMP, might actually be hopping between dimensions via these quantum-scale wormholes. It's a twist on the hidden sector idea, where dark matter inhabits a parallel universe with its own forces, occasionally leaking into ours through space-time defects. Imagine ants crawling on a sheet of paper that occasionally dip into a fold you didn't notice. Dark matter might be doing the same, with wormholes as its secret passageways. Observational clues could already be hiding in plain sight. Astronomers have detected bizarre gamma-ray excesses from galaxies like Andromeda, emissions that defy conventional explanations. One tantalizing possibility: dark matter particles colliding and annihilating as they pass through wormhole throats, releasing bursts of energy. There's also the curious case of dark stars, hypothetical celestial objects powered not by nuclear fusion, but by the annihilation of dark matter in their cores. Could these stars form around wormhole endpoints where dark matter density spikes to extreme levels? Not everyone's convinced, of course. Critics argue that linking dark matter to wormholes piles speculation atop speculation, with no direct evidence to tie the two together. But proponents counter that anomalies like unexpected gravitational lenses where light bends in ways that suggest hidden, compact masses might one day betray the presence of wormholes lurking in dark matter-rich regions. Future telescopes like the Vera Rubin Observatory could spot these subtle distortions, offering the first hints of something far weirder than dark matter alone. Whether this theory holds up or not, it underscores a thrilling truth. The universe's greatest enigmas might not be separate puzzles, but pieces of a larger, more mysterious whole. Dark matter and wormholes could be threads in the same cosmic tapestry, one we've only just begun to untangle. And that's the kind of idea that keeps astronomers and physicists awake at night, searching the darkness for answers. The holographic principle turns our view of reality inside out. What if the three-dimensional universe we see is just a projection, like a movie screen displaying a world that's actually encoded on a two-dimensional surface? This mind-bending idea, born from black hole physics, suggests that spacetime itself might be a hologram, with all its depth and complexity emerging from information painted on a distant, flat boundary. Now imagine applying this to wormholes. Instead of being physical tunnels through space, they could be computational shortcuts, glitches in the cosmic code where two distant points on the holographic surface are secretly linked, making their projections overlap in higher dimensions. Think of it like a video game where the graphics engine renders a vast open world, but behind the scenes, it's all just data on a chip. A wormhole, in this analogy, wouldn't be a tunnel in the game world itself, but a clever trick where the engine skips, rendering the distance between 2 points altogether. The player, or in this case a spaceship, would simply disappear from one location and reappear in another, with no physical journey in between. The holographic principle suggests spacetime might work the same way, with wormholes as optimized data pathways in the universe's underlying program. This perspective could solve one of wormhole theory's biggest headaches: stability. If a wormhole isn't a physical structure but a computational link, it wouldn't need exotic matter to prop it open. The holographic code could simply allow certain points in space to share information instantaneously, much like entangled particles do in quantum mechanics. In fact, there's a tantalizing parallel here with the ER=EPR conjecture, the idea that entanglement and wormholes are two sides of the same coin. Both theories hint that the universe's deepest connections might not happen in the space we see, but in the hidden layer beneath it. But how would a holographic wormhole look to someone passing through? If spacetime is a projection, stepping into one might feel less like traveling and more like being rewritten. Your information, every atom, every memory, could be transcribed onto the lower dimensional boundary, then reconstituted at the exit point. It's a far cry from the starry tunnels of sci-fi, but no less astonishing. You wouldn't traverse space, you'd be reassembled by the universe itself, like a fax sent across the cosmos. Critics argue that this is just another layer of abstraction, pushing the problem into the realm of pure math. Yet supporters counter that the holographic principle could simplify wormhole physics dramatically. Instead of wrestling with gravity and exotic matter, we might only need to understand how information flows on the universe's fundamental surface. Future experiments with quantum gravity or higher dimensional simulations could put this idea to the test, searching for telltale glitches in spacetime's pixelation where holographic wormholes might lurk. Whether it's the ultimate answer or just another stepping stone, the holographic view reshapes the quest for wormholes. It's no longer about bending space, it's about decoding the universe's deepest language, where distance and connection might just be illusions waiting to be hacked. And that's a frontier where physics and philosophy collide in the most thrilling way possible. If string theory paints the universe as a symphony of vibrating strings, loop quantum gravity offers a radically different score, one where space itself is stitched together from tiny, woven loops. This theory abandons the idea of smooth, continuous space-time, proposing instead that reality is woven from discrete, indivisible threads, like a cosmic fabric built from microscopic stitches. And in this framework, wormholes aren't tunnels carved through space, they're knots where those loops twist back on themselves, creating shortcuts in the very weave of the universe. The key lies in how loop quantum gravity reimagines space-time structure. Instead of a malleable sheet bent by gravity, space is a network of interlinked loops, each carrying a quantum of area or volume. Picture a sprawling mesh of interconnected threads, where every intersection represents a tiny grain of space. Now, imagine two distant points in this network suddenly pinching together as loops rearrange, forming a bridge where none existed before. It's as if the stitches of reality themselves could be tugged and tied into a new configuration, bypassing the usual constraints of distance. What makes this approach so compelling is its potential to sidestep the need for exotic matter. In string theory, stabilizing a wormhole often requires hypothetical substances with negative energy. But in loop quantum gravity, the wormhole's stability could emerge naturally from the way space's loops knot and unknot. The tunnel isn't held open by external forces, it's woven into the universe's fundamental structure, like a braid that can't unravel without breaking the rules of quantum geometry. The catch: these wormholes would likely exist at scales far smaller than an atom, flitting in and out of existence as loops fluctuate. Scaling them up to human traversable sizes would demand energies beyond anything we can currently conceive. Yet some models suggest that under extreme conditions like the heart of a collapsing black hole, these quantum loops might twist into macroscopic bridges. It's a tantalizing possibility. The universe's most destructive phenomena could spawn gateways to elsewhere, not by bending space but by rewriting its very code. Contrast this with string theory's extra dimensions and holographic brains. Where string theory seeks unity by adding layers to reality, loop quantum gravity strips space down to its barest threads. Both aim to reconcile relativity with quantum mechanics, but they chart wildly different paths. For wormholes, that means two competing visions, one where tunnels are woven from hidden dimensions, and another where they're knots in space's quantum fabric. The implications ripple outward. If loop quantum gravity is correct, then wormholes might not be rare cosmic flukes, but inevitable features of a granular universe. Every cubic centimeter of space could harbor flickering micro-wormholes, brief portals where loops momentarily knot. Advanced civilizations might one day learn to comb space's loops into stable configurations, engineering wormholes as routinely as we build bridges. Of course, skeptics point out that loop quantum gravity remains untested, its predictions hovering beyond today's experimental reach, but the theory's elegance lies in its minimalism. No extra dimensions, no exotic matter, just space itself revealing its quantum soul. Whether it ultimately unlocks wormholes or not, it challenges us to rethink reality's fabric, not as something we move through, but as something we might one day learn to knot. What if traversing a wormhole wasn't just about moving through space, but about processing information itself? At the bleeding edge of theoretical physics, some scientists speculate that wormholes could function as nature's ultimate quantum computers, harnessing entanglement and spacetime's hidden geometry to perform calculations no silicon chip could ever match. It's a concept that blurs the line between gravity and computation, where the universe's most enigmatic structures might double as cosmic processors. Here's how the pieces fit together. Quantum computers today rely on qubits particles that can be in multiple states at once, linked through entanglement to perform parallel calculations. But what if that entanglement isn't just a useful quirk of quantum mechanics, but a physical bridge through spacetime? Recall the ER=EPR conjecture, where entangled particles are connected by microscopic wormholes. Scale this up, and a traversable wormhole could become a circuit of unimaginable power, with every particle passing through its throat carrying information that's instantly accessible at the other end. It's not just data transfer, it's reality itself performing the computation. Black holes add a tantalizing twist. According to the holographic principle, all the information swallowed by a black hole isn't lost, it's smeared across its event horizon like a cosmic hard drive. Now imagine a wormhole linking two black holes. Calculations suggest their connected horizons could act like quantum gates, processing information through the wormhole's geometry. The math reveals something astonishing. The wormhole's length and curvature might directly correspond to the complexity of the computation, as if spacetime itself were solving equations by reshaping its fabric. The implications for the black hole information paradox are profound. If matter falling into a black hole isn't destroyed but encoded on its horizon, a wormhole could be the universe's way of preserving and processing that data. Picture an entangled pair of black holes, their wormhole throat acting as a quantum tunnel where information is scrambled and reassembled like a cosmic encryption protocol. This wouldn't just resolve the paradox, it would suggest that black holes and wormholes are integral parts of the universe's information architecture, performing operations we're only beginning to fathom. Yet the wildest possibility lies in scalability. Could a sufficiently advanced civilization engineer wormholes as programmable processors? Theoretically, yes. By manipulating entangled black holes or stabilizing quantum foam, they might create a network where spacetime itself executes algorithms. Input a problem at one end, and the wormhole's geometry evolves to spit out the solution at the other, with no classical computation in between. It's computation without computation, where the answer emerges from the shape of reality. Of course, this remains speculative. No one's building wormhole quantum computers anytime soon, but the theory offers something equally valuable, a new lens to view spacetime's deepest mysteries. Whether wormholes are cosmic shortcuts or nature's quantum processors, they're forcing us to rethink not just how the universe works, but how it computes. And that's a revolution waiting to happen. What if every decision you've ever made, every path taken or not taken, exists simultaneously in an infinite web of parallel realities? The multiverse theory suggests just that, painting a cosmos where countless versions of history unfold in branching timelines. Now, imagine wormholes threading through this labyrinth, not just connecting distant points in our universe, but stitching together entirely separate realities. These wouldn't be mere space-time shortcuts, they'd be portals to alternate versions of Earth, alien civilizations that never arose, or cosmic epochs long gone. The idea transforms wormholes from interstellar highways into bridges between dimensions, where the laws of physics themselves might shift from one step to the next. The many worlds interpretation of quantum mechanics gives this theory a spine. Every quantum event, a particle spinning left or right, a photon passing through a slit, splits reality into divergent branches. Normally, these worlds remain forever separate, like pages in an endless book no one can turn. But a wormhole could pierce through those pages, linking chapter to chapter. Picture a tunnel where one end opens in a universe where dinosaurs never went extinct, and the other emerges in a reality where humans colonized Mars centuries ago. The implications are dizzying. Travel through such a wormhole wouldn't just cross space, but rewrite your very context, dropping you into a timeline where the rules, even the history you know, might be unrecognizable. This could also reshape the Fermi paradox, the haunting question of why, in a universe teeming with billions of stars, we've found no trace of alien life. If advanced civilizations discovered multiverse wormholes, they might have abandoned our universe altogether, migrating to realities with richer resources or more hospitable physics. Or perhaps contact has already happened, just not in our timeline. The absence of aliens wouldn't mean they don't exist, but that they're thriving in branches of the multiverse we can't yet access. Wormholes, in this view, might explain the silence not as a sign of solitude, but as evidence of a cosmos vaster and stranger than we'd ever imagined. Yet the challenges are as profound as the possibilities. A multiverse wormhole would need to navigate not just space-time, but an entirely different set of physical constants. In some universes, gravity might be stronger. In others, light could move slower. Traversing such a tunnel might require surviving a gauntlet of shifting forces, like a ship sailing through a storm where the very nature of weather changes mid-voyage. Some models suggest these wormholes could only stabilize in regions where quantum fluctuations align just right, a cosmic needle in a haystack scenario. Others argue that the energy required to keep a multiverse bridge open would dwarf the output of entire galaxies. But here's the kicker. If even one civilization cracked the code, the implications would ripple across realities. Wars over alternate resources, alliances spanning timelines, the spread of ideas between versions of Earth, wormholes could turn the multiverse into a living network, humming with the traffic of infinite possibilities. Until then, the theory remains a gateway to the grandest what-ifs physics has to offer, a reminder that our universe might not just be one home among the stars, but one thread in a tapestry woven from endless variations of itself. And somewhere in that tapestry, another version of you might be wondering the same thing. The collision of two neutron stars sends shockwaves through space-time, ripples so powerful they bend the fabric of reality itself. These cosmic crashes are among the most violent events in the universe, unleashing energies that dwarf a supernova. But hidden in that chaos could be something even more extraordinary, the birth of a wormhole. When ultra-dense objects like neutron stars or primordial black holes merge, their immense gravitational fields don't just create gravitational waves. They might twist space-time so severely that it momentarily tears, forming a tunnel between distant points. It wouldn't be a deliberate engineering feat, but a fleeting accident of physics, like lightning cracking open the sky to reveal something unimaginable. The math behind this possibility is as brutal as it is beautiful. Einstein's equations show that when two ultra-compact objects spiral into each other, their combined mass warps space-time into shapes far stranger than a simple black hole. During the final milliseconds before collision, tidal forces stretch and compress space like taffy, potentially pinching it into a temporary throat, a wormhole that might last only microseconds before collapsing into a singularity. The key lies in the object's spin. If the merging remnants are rotating fast enough, their centrifugal force could counteract gravity's crush just long enough for a wormhole to flicker into existence. Picture two whirlpools merging in a stormy sea. At the moment they unite, the water between them might form a brief tunnel before collapsing under its own weight. Gravitational wave detectors like LIGO and Virgo could hold the clues to spotting these ephemeral wormholes. When black holes or neutron stars collide, they emit characteristic chirp signals that match predictions with stunning accuracy. But what if some mergers produced anomalies? A wormhole's brief appearance would distort these gravitational waves in telltale ways, adding echoes or frequency glitches as space-time rearranges itself. It's like listening to a song where a single note suddenly plays backward, a subtle but unmistakable hint that something extraordinary happened. In 2017, LIGO detected a neutron star merger accompanied by a gamma-ray burst. While no wormhole signatures were found, future upgrades might catch whispers of spacetime's most elusive shortcuts. Primordial black holes, hypothetical relics from the universe's first second, add another layer of intrigue. Unlike stellar black holes, these ancient objects could be any size, from asteroid mass to planet-sized. If two primordial black holes merged in the early universe, their extreme density might have forged wormholes that persisted long enough to influence cosmic evolution. Some theorists even speculate that such wormholes could explain the universe's mysterious homogeneity, the way distant regions appear eerily similar despite never being in contact. A network of primordial wormholes might have connected them, like underground roots secretly nourishing a forest. The stakes here aren't just academic. If natural wormholes form during extreme astrophysical events, even briefly, they'd prove that space-time is far more malleable than we thought. Advanced civilizations might learn to harvest these cosmic glitches, stabilizing them with technology we can't yet fathom. Or perhaps the universe is already threaded with ancient wormholes from long-ago collisions, their endpoints hidden in plain sight. Every time gravitational wave detectors ping with a new merger alert, they're not just recording death throes, they might be capturing the birth cries of spacetime's strangest offspring. And that's a signal worth listening for. The Big Bang wasn't just the beginning of our universe, it might have been the ultimate wormhole factory. Picture the newborn cosmos, a seething plasma of unimaginable energy, space-time stretched and twisted like taffy in those first fleeting moments. Some theories suggest that in that primordial chaos, defects and fractures could have formed in the very fabric of reality, leaving behind tunnels that stretch not just across space but between universes themselves. These wouldn't be your garden-variety wormholes. They'd be cosmic relics forged in the fires of creation, possibly threading through higher dimensions or even linking our universe to others in a vast multiverse. One compelling framework is conformal cyclic cosmology, or CCC, proposed by physicist Roger Penrose. In this mind-bending model, the universe doesn't have a single beginning and end, it's a cycle of endless rebirth. Each aeon begins with its own Big Bang, which is actually the far future death of the previous universe, stretched and transformed through a process called conformal rescaling. And here's where wormholes come in. The transition between eons might not be perfectly smooth. Quantum fluctuations or gravitational echoes from the prior universe could imprint themselves as irregularities in the new one, like cosmic scars. Some of these scars, Penrose suggests, could take the form of space-time tunnels, wormholes that serve as bridges not just across space, but across time and even between iterations of reality. Imagine stepping through a wormhole and emerging not in another galaxy, but in a universe where the laws of physics are subtly or drastically different. Cyclic cosmology offers another variation on this theme. In these models, the universe expands, contracts, and explodes anew in an endless loop. But instead of resetting completely, each cycle might preserve traces of the one before. Wormholes formed in the collapse of a previous universe could survive the Big Bang, acting as umbilical cords tethering each new incarnation to its ancestors. It's as if the universe has a memory, and wormholes are its way of whispering secrets across the eons. Of course, testing these ideas is a monumental challenge. If such wormholes exist, they'd likely be crumpled and distorted by 14 billion years of cosmic expansion, like ancient roads buried under layers of geological time. But there might be ways to hunt for them. Penrose and others have scoured the cosmic microwave background, the afterglow of the Big Bang, for telltale rings or anomalies that could hint at gravitational waves from a prior eon. These patterns, if found, might betray the presence of wormholes woven into the universe's deepest foundations. The implications are staggering. If wormholes from the Big Bang endure, they could be more than just curiosities. They might be the universe's way of recycling itself, stitching each new iteration to the ones before and after. Whether they lead to other realities, other times, or just the hidden corners of our own cosmos, one thing's certain: the Big Bang didn't just create space and time. It might have built the tunnels that connect them all. Plasma, the fourth state of matter, is more than just the stuff of stars. It could be the key to unlocking wormhole physics right here in the lab. Unlike the exotic matter or cosmic strings we've explored so far, plasma offers something rare, a tangible, manipulable medium where wormhole-like structures might emerge on human scales. Picture a donut-shaped vortex of superheated gas, spinning at unimaginable speeds under the grip of powerful magnetic fields. In certain high-energy experiments, these plasma toroids don't just behave like fluid dynamics puzzles, they warp space around them in ways that eerily echo the equations of traversable wormholes. The magic lies in plasma's dual nature. As a swirling soup of charged particles, it responds fiercely to electromagnetic forces, bending and twisting into configurations that defy classical geometry. Under extreme conditions like those in tokamaks, the donut-shaped reactors used for nuclear fusion research plasma can form self-stabilizing structures called spheromax. These aren't just random blobs of hot gas. They're intricate, nested magnetic geometries that some physicists argue could mimic the spacetime curvature of a wormhole's throat. The math reveals a striking parallel. The way magnetic field lines twist and knot in these plasmas mirrors the theoretical warping needed to keep a wormhole open. It's as if nature is hinting that the recipe for spacetime shortcuts might be hiding in plain sight, written in the language of charged particles and magnetic vortices. Laboratory experiments have already glimpsed hints of this phenomenon. In 2019, researchers at the Princeton Plasma Physics Laboratory observed bizarre particle behavior in their tokamak trajectories that didn't align with standard plasma models. Some theorists suggested these anomalies could stem from microscopic regions where the plasma's magnetic geometry effectively folds space, creating transient pathways akin to quantum-scale wormholes. While far from interstellar tunnels, these fleeting structures might be the first experimental evidence that wormhole physics isn't confined to black holes or cosmic strings. It could be brewing in our fusion reactors, waiting to be harnessed. The real game changer, unlike hypothetical exotic matter, plasma is something we can actually produce and control. Advanced plasma experiments could one day engineer stable configurations where these wormhole-like effects become measurable, perhaps even usable. Picture a future where magnetic confinement doesn't just generate clean energy, but twists space-time itself into experimental gateways. The challenges are immense, of course. Stabilizing these structures for more than milliseconds would require energies rivaling those of stars, and scaling them up to macroscopic sizes is a hurdle we can't yet clear. But the mere possibility reshapes the quest for wormholes from a cosmic scavenger hunt into something closer to engineering. Critics argue that plasma-based wormholes are little more than mathematical curiosities, clever analogies without real spacetime significance. Yet the parallels are too compelling to ignore. Whether these experiments are simulating wormholes or accidentally creating them, they're proving one thing. The universe's most profound mysteries might not lie light years away, but in the superheated heart of our own laboratories. And that's a revelation hot enough to match the plasma itself. What if consciousness isn't confined to the brain, but woven into the fabric of space-time itself? This radical idea bridges the gap between physics and philosophy, suggesting that wormholes, those cosmic shortcuts through reality, might play a role in how awareness emerges. One of the most controversial takes comes from physicist Roger Penrose and anesthesiologist Stuart Hameroff, whose ORCH or theory proposes that consciousness arises from quantum vibrations inside the brain's microtubules, tiny protein structures within neurons. But here's the twist: these quantum processes might rely on spacetime itself, possibly even microscopic wormholes, to preserve coherence long enough for subjective experience to form. Penrose's argument hinges on a fundamental problem. How does the brain, a warm, wet, noisy system, avoid quantum decoherence, the constant disruption that usually destroys quantum states in everyday conditions? His answer is as bold as it is speculative: gravity-induced collapses. In this view, consciousness isn't just electrical signals firing. It's a symphony of quantum computations happening at the Planck scale, where spacetime's geometry is no longer smooth but foamy and fluctuating. And if spacetime can form fleeting wormholes at this scale, as quantum gravity theories suggest, they might act as conduits, linking quantum states across neurons before they collapse into definite perceptions. It's as if every thought or sensation is a quantum decision made possible by spacetime's hidden tunnels. Critics, of course, are quick to dismiss ORCH or. Most neuroscientists argue that consciousness likely emerges from complex neural networks, not quantum magic. Decoherence in the brain would obliterate delicate quantum states faster than they could influence cognition. Even Penrose admits the theory is fringe, yet its implications for wormholes are too intriguing to ignore. If consciousness somehow taps into spacetime's deepest structures, could advanced civilizations harness this link to communicate or travel through wormholes mentally? It sounds like science fiction, but some theorists speculate that an appropriately tuned brain or artificial intelligence might detect or even stabilize microscopic wormholes through pure thought, bending perception and reality in ways we can't yet fathom. The wildest extension of this idea comes from panpsychism, the philosophical view that consciousness is a fundamental property of the universe, like mass or charge. In this framework, wormholes wouldn't just be tools for travel, they might be conduits for subjective experience itself, linking minds across space and time. Imagine a wormhole not as a tunnel for spaceships, but as a bridge between sentient beings, allowing direct sharing of thoughts or emotions. It's a notion that blurs the line between physics and mysticism, but it raises a profound question. If spacetime can warp, why not consciousness too? Skeptics rightly demand evidence, and so far, ORCH has little beyond mathematical elegance and speculative appeal. Yet the theory's value lies in its audacity. By daring to connect consciousness to spacetime's quantum fabric, it challenges us to rethink not just how we perceive reality, but how reality might perceive us. Whether wormholes play any role in awareness remains uncertain, but the mere possibility stretches our understanding of both mind and cosmos to their breaking points. And sometimes that's where the most thrilling discoveries begin. Dark energy, the mysterious force accelerating the universe's expansion, might be doing far more than just pushing galaxies apart. It could be the invisible architect holding open wormholes across the cosmos. Picture the universe not just stretching, but actively threading itself with hidden tunnels where dark energy's repulsive force counteracts gravity's crush, turning unstable spacetime defects into durable shortcuts. This theory flips conventional wisdom on its head. Instead of wormholes requiring exotic engineering, they might emerge naturally as cosmic expansion sculpts the fabric of reality itself. The math behind this idea hinges on dark energy's peculiar properties. Unlike gravity, which pulls matter together, dark energy generates negative pressure, a kind of anti-gravity that pushes space outward. In the seething quantum foam of the early universe, tiny wormholes could have formed spontaneously, only to be immediately crushed by gravitational forces. But if dark energy permeated these fledgling tunnels, its repulsive effect might have propped them open like cosmic bellows, resisting collapse. Over billions of years, as the universe expanded, these stabilized wormholes could have stretched alongside it, growing from microscopic quirks to potential galaxy-spanning bridges. Observational clues might already exist in the universe's emptiest regions, cosmic voids, these vast bubble-like expanses where galaxies are scarce and dark energy dominates, could harbor wormholes disguised as gravitational anomalies. Imagine a void where the pull of matter doesn't quite match predictions, not because of unseen mass, but because a wormhole's throat siphons gravitational influence elsewhere. Telescopes mapping the motions of galaxies near voids have spotted peculiar velocity patterns that defy standard models. Could these be subtle fingerprints of wormholes redirecting gravity through hidden corridors? The Planck satellite's cosmic microwave background data adds another layer of intrigue. Certain temperature fluctuations in the afterglow of the Big Bang align eerily with theoretical models of wormhole-influenced spacetime. These patterns, resembling concentric rings or unexpected cold spots, might trace where primordial wormholes left imprints on the universe's infancy. Future missions like the European Space Agency's Euclid telescope could take this search further, scanning voids for telltale distortions in starlight or anomalies in dark energy distribution. Of course, skeptics argue that attributing cosmic quirks to wormholes is premature when simpler explanations exist. But proponents counter that dark energy's dominance makes it a natural candidate for spacetime engineering, no exotic matter required. If the universe itself is constantly stretching space, why wouldn't it leave behind wrinkles in the form of wormholes? The answer could redefine not just how we traverse the cosmos, but how we understand its very expansion. After all, if dark energy can push galaxies apart, who's to say it can't also stitch them together? What if spacetime isn't a static stage, but a fluid one so perfectly smooth and frictionless that it could ripple with unseen currents? Superfluid vacuum theory proposes exactly that, reimagining the universe as a quantum superfluid, a medium where particles move without resistance and where defects in the flow could twist into wormholes. Picture the cosmos not as an empty void, but as an ultra-cold, ultra-precise liquid, its subtle undulations giving rise to everything from galaxies to gravity. And within this fluid, like whirlpools in a stream, vortices might spiral into tunnels, wormholes formed not by gravity alone, but by the very texture of spacetime itself. The roots of this idea stretch back to Einstein, who once speculated that spacetime might behave like a fluid. But superfluid vacuum theory takes it further, drawing inspiration from Bose-Einstein condensate's laboratory states of matter where atoms chill to near absolute zero and merge into a single quantum wave. In these bizarre fluids, vortices can form that are eerily stable, their cores empty of matter yet defined by the swirling currents around them. Translate this to spacetime, and similar vortices could emerge as microscopic wormholes, their throats held open not by exotic matter, but by the superfluid's own quantum rules. It's as if the universe has a hidden viscosity, a subtle stickiness that allows it to fold into shortcuts when stirred just right. Quantum turbulence adds another layer to this analogy. In superfluid helium, chaotic tangles of vortices can knot and reconnect, creating fleeting structures that resemble fractal labyrinths. If spacetime behaves similarly, then the quantum foam, that seething Planck-scale froth, might not just be random noise. It could be a turbulent sea of microscopic wormholes, constantly forming and dissolving like bubbles in a boiling pot. Some models even suggest that under extreme conditions, like near a black hole's event horizon, these turbulent vortices could align into macroscopic tunnels, stitching together distant regions of space like threads through fabric. The parallels to cosmic strings are striking. Both theories propose that spacetime defects could birth wormholes, but while cosmic strings are relics of the early universe's phase transitions, superfluid vortices would be ongoing phenomena, dynamic and ever-shifting. Imagine a river where eddies occasionally spiral deep enough to pierce through the riverbed, creating temporary channels between distant points. Superfluid spacetime might do the same, with quantum turbulence weaving wormholes into existence as naturally as water forms whirlpools. Critics argue that treating spacetime as a superfluid is a stretch, given the lack of direct evidence. Yet the theory's elegance lies in its economy. It unifies the behavior of quantum fields with the geometry of relativity, offering a framework where wormholes emerge from first principles rather than ad hoc assumptions. If correct, it would mean that wormholes aren't rare anomalies, they're woven into the universe's fluid dynamics, waiting to be harnessed by anyone who learns to navigate the currents of spacetime itself. Whether superfluid vacuum theory holds up or not, it challenges us to rethink the nature of reality. The universe might not be built on rigid, unyielding space and time, but on something far more malleable, a quantum fluid where every ripple, every vortex could be a doorway to elsewhere. And that's a vision as breathtaking as it is bizarre. Neutrinos are the universe's ultimate ghost particles, so elusive they pass through planets like moonlight through glass. But their strangest trick isn't just slipping unnoticed through matter. It's their ability to shape-shift mid-flight, flipping between three distinct flavors: electron, muon, and tau. This phenomenon, called neutrino oscillation, has long puzzled physicists. Now, some theorize these quantum metamorphoses might be more than just subatomic quirks. They could be evidence of neutrinos briefly darting through hidden dimensions or even microscopic wormholes. The math behind this idea is as elegant as it is radical. Neutrinos oscillate because their mass states the quantum bedrock beneath their flavors don't perfectly align with how we detect them. Normally, this is explained by quantum mechanics alone. But what if there's more to the story? Imagine a neutrino's path through space isn't a straight line, but a series of hops where it occasionally slips into an extra-dimensional shortcut. Each time it ducks into this hidden realm, even for an instant, its properties might shift in ways we perceive as flavor changes. It's less like a particle changing costumes and more like one taking a detour through a higher dimensional tunnel, emerging subtly altered. This theory gains traction when you consider the sterile neutrino, a hypothetical fourth flavor that doesn't interact with any known force except gravity. Experiments like LSD and Mini-BuNi have detected anomalous oscillation patterns that suggest something's missing from the standard model. Sterile neutrinos, if real, could be oscillating into dimensions we can't probe or even tunneling through Planck-scale wormholes. Picture a game of peekaboo where the neutrino vanishes into the fabric of spacetime itself, only to pop back out wearing a different quantum face. The data isn't conclusive yet, but the anomalies are tantalizing enough to keep physicists hunting. Critics argue that invoking extra dimensions or wormholes is overcomplicating a phenomenon that might just need tweaks to existing neutrino physics. Yet supporters counter that nature rarely favors simplicity when weirdness will do. After all, neutrinos already defy expectations. They're billions of times lighter than electrons, barely interact with matter, and now they might be cosmic hitchhikers riding wormholes we can't see. If true, every neutrino detection could be a glimpse into the universe's hidden architecture, where the tiniest particles are the boldest explorers, charting paths through dimensions beyond our own. What makes this idea so compelling isn't just the how, but the why. If neutrinos are flickering through wormholes even fleetingly, it would mean these spacetime tunnels aren't rare cosmic oddities. They're woven into the fabric of everyday particle physics. Every second, trillions of neutrinos from the Sun alone might be surfing these microscopic shortcuts, their oscillations whispering secrets about the universe's deepest layers. And that's a signal worth listening to, one ghostly particle at a time. Quantum tunneling is one of the strangest behaviors in physics, particles vanishing through barriers they should never overcome, like ghosts walking through walls. Electrons trapped in an atom suddenly appearing outside it, or alpha particles escaping a nucleus despite being locked in by unimaginable forces. Now imagine scaling this bizarre phenomenon up, not just to particles but to spacetime itself. Could the universe have its own version of quantum tunneling, where entire regions of reality bypass the usual rules of distance and time? That's the audacious idea behind wormholes as spacetime tunnels, bridges forged not by gravity alone, but by the same quantum sorcery that lets particles defy impossibility. At the heart of this theory lies a radical reimagining of Feynman diagrams, those squiggly line drawings physicists used to map particle interactions. Normally, these diagrams show particles exchanging virtual photons or gluons, ephemeral messengers that flicker in and out of existence. But if you stretch this idea to cosmic scales, the same quantum uncertainty might allow spacetime itself to borrow energy, warping into fleeting tunnels that bypass classical distances. Picture a Feynman diagram redrawn on the fabric of the universe. Instead of electrons swapping photons, two black holes could exchange a wormhole, their gravitational fields twisting space into a temporary shortcut. It's as if the cosmos has a hidden accounting system where spacetime can go briefly into debt, bending into a tunnel before snapping back to equilibrium. The math behind this is as elegant as it is mind-bending. Quantum tunneling relies on wave functions, probabilistic descriptions of where particles might be. In standard tunneling, there's always a tiny chance a particle's wave function will leak through a barrier, allowing it to emerge on the other side. Apply this to spacetime, and the wave function becomes a description of possible geometries. Just as an electron can tunnel through an energy barrier, spacetime might tunnel through a distance barrier, collapsing the path between 2 points into a wormhole. The probabilities are vanishingly small, but in a universe as vast and ancient as ours, even the unlikeliest events can become inevitable. Critics argue that scaling quantum effects to macroscopic objects is a leap too far. After all, tunneling works for particles because they're governed by probability clouds, not definite paths. Spacetime, on the other hand, seems stubbornly classical in its behavior. Yet supporters counter that at the Planck scale, where quantum gravity reigns, spacetime itself may be frothy and uncertain, more a network of probabilities than a fixed stage. In this view, wormholes wouldn't be rare anomalies, but everyday quantum fluctuations, most too small and fleeting to notice. The challenge isn't whether they exist, but whether we could ever stabilize and enlarge one without it collapsing like a soap bubble. The implications ripple outward. If spacetime can tunnel, then wormholes might not need exotic matter or cosmic strings, just the right quantum conditions to tip the odds. Advanced civilizations might learn to seed these tunnels, coaxing spacetime into borrowing energy in controlled ways. Or perhaps natural wormholes already flicker into existence in extreme environments like neutron star mergers or black hole collisions, hidden in the quantum static of the universe's most violent events. Whether this theory holds up or not, it reshapes how we see the cosmos. Quantum tunneling reminds us that reality has a fuzziness to its rules, a flexibility that defies common sense. Scale that up, and the universe itself might be far more negotiable than we ever dreamed, not a rigid grid of distances and times, but a shimmering web of possibilities, where even the longest journeys could one day be shortcuts. Einstein's general relativity has reigned supreme for over a century, dictating how we understand gravity and the shape of spacetime. but what if it's not the full story? Modified Newtonian dynamics, or MND, offers a radical alternative. This theory suggests that on cosmic scales, gravity behaves differently than relativity predicts, eliminating the need for dark matter to explain galaxy rotations. And here's the twist. In some MND-based models, wormholes might emerge naturally, no exotic matter required. Picture a universe where spacetime's shortcuts aren't cosmic rarities, but inevitable features baked into the fabric of gravity itself. MND's secret lies in tweaking gravity's rules at low accelerations. Instead of invoking invisible dark matter to explain why stars at galaxies' edges orbit faster than expected, MND proposes that gravity strengthens slightly where relativity says it should weaken. This adjustment bends spacetime in novel ways, and under certain conditions, those bends could fold into wormholes. Imagine pressing your thumb into a soft rubber sheet, not enough to tear it, but enough to make two distant points nearly touch. In MND framework, spacetime might fold like that rubber sheet under gravity's revised influence, forming bridges without the need for negative energy or other exotic ingredients. But does this hold up to scrutiny? Proponents point to MND's success in predicting galaxy rotations without dark matter as a hint that its spacetime geometry could harbor surprises. Some solutions to MND equations indeed produce wormhole-like structures, often as topological defects left over from the universe's early phases. These wouldn't be the traversable wormholes of sci-fi, more like fossilized spacetime wrinkles, but their existence would challenge our assumptions about what gravity can and can't do. Critics, however, highlight gaps. MND struggles with galaxy clusters and the cosmic microwave background, where dark matter's influence is harder to dismiss. Worse, MND-based wormholes often rely on untested assumptions about how gravity behaves in extreme regimes. While general relativity's wormholes demand exotic matter, MND might demand equally controversial tweaks to gravity's fundamental laws. It's a trade-off. Ditch one mystery for another. Observational tests could tip the scales. If MND is correct, certain wormholes might leave faint gravitational imprints, subtle lensing anomalies, or unexpected stellar motions near galactic centers. Future telescopes like the LSST or gravitational wave detectors tuned to low-frequency signals might spot these fingerprints. Until then, MND wormholes remain tantalizing what-ifs, reminders that our grasp of gravity and the shortcuts it might allow is still evolving. Whether they're real or not, they force us to ask, is spacetime's rulebook truly written in Einstein's hand, or are there pages we've yet to uncover? The Fermi paradox has haunted astronomers for decades. If the universe is teeming with stars, why does it feel so empty? One possible answer lies in the very technology that could render traditional space travel obsolete: wormholes. Imagine a civilization millions of years ahead of us, having long surpassed the need for sluggish rockets or generational ships. Instead, they've mastered spacetime itself, weaving networks of wormholes so efficient that interstellar voyages are as routine as subway rides. If such civilizations exist, their absence from our telescopes isn't proof they're not out there. It's evidence they've moved beyond the crude methods we're still using to search for them. Consider the energy signatures we typically hunt for radio transmissions: Dyson spheres harvesting starlight, or the infrared glow of megastructures. A wormhole-based society would leave none of these traces. Why build a Dyson sphere around a star when you can tap the gravitational energy of a black hole to stabilize your wormholes? Instead of flooding the cosmos with detectable waste heat, their infrastructure might be nearly invisible, operating in dimensions or frequencies we can't yet perceive. The equivalent wouldn't be a bustling highway, it'd be a hidden subway system, its entrances and exits camouflaged by advanced physics or tucked inside naturally occurring cosmic structures like neutron stars or nebulae. Then there's the scale of time. Wormholes could resolve Fermi's paradox by collapsing the distances not just in space but in time. A civilization that cracks wormhole travel early in its development might rapidly expand, explore, and then retreat into a post-physical existence within a cosmic network before younger species like ours even glance at the stars. They wouldn't just be elsewhere, they'd be elsewhen, their activities compressed into brief, hyper-advanced epochs separated by eons of silence. The universe might be littered with their dormant gateways, waiting for someone to stumble upon the right activation code. This isn't just speculation, it reshapes how we should search. Instead of scanning stars for technosignatures, we might look for gravitational anomalies, stars orbiting nothing, unexplained lensing patterns, or black holes with peculiar accretion disks that resemble artificial docking ports. The Breakthrough Listen project's recent shift to include interstellar communication networks in its search criteria hints at this evolving approach. After all, if you've already built the ultimate shortcut, why would you bother leaving breadcrumbs in the void? The silence isn't a sign of absence, it's the signature of a universe where the truly advanced have already checked out, leaving us to decipher the echoes of their wormhole highways. Quantum fields are the universe's unseen scaffolding, a roiling sea of energy that gives rise to everything from electrons to galaxies. Normally, we think of particles as tiny dots, but in quantum field theory, they're more like ripples on this infinite ocean, brief disturbances in an otherwise humming background. Now imagine that same ocean occasionally twisting itself into knots, forming temporary whirlpools that stitch distant points together. That's the essence of wormholes in quantum field theory. Not cosmic engineering projects, but spontaneous fluctuations, as fleeting and unpredictable as virtual particles popping in and out of existence. These quantum wormholes wouldn't be the grand, star-spanning tunnels of sci-fi. They'd be microscopic, likely lasting only fractions of a second before vanishing back into the foam of spacetime. But their theoretical existence forces physicists to confront one of the most notorious problems in modern physics: infinity. Wormhole solutions in general relativity often come with a nasty side effect: infinite curvature at their throats, rendering the math nonsensical. Here's where renormalization, quantum field theory's greatest trick, might save the day. This process lets physicists sweep infinities under the rug by carefully redefining how they measure energy and scale, effectively subtracting the nonsense to reveal meaningful predictions underneath. It's the reason we can calculate anything in quantum electrodynamics despite similar infinite energies lurking in the equations. Visualize it like this: a quantum field's fluctuations are like static on an old TV screen. Most of the time, it's just noise, but occasionally patterns emerge, a face, a shape. Quantum wormholes would be those rare, coherent patterns, momentary alignments where the field's chaos briefly conspires to form a tunnel. Renormalization acts like a filter, tuning out the deafening static to isolate the signal. Without it, these wormholes would be lost in a sea of infinite energies, their physics impossible to untangle. The implications ripple far beyond theory. If quantum fields can spontaneously birth wormholes, even at scales too small to measure, it suggests spacetime is far more dynamic than we ever imagined. Dark energy, the vacuum's inherent energy, might owe its repulsive force to these microscopic spacetime defects, their collective influence stretching the universe apart. Some models even propose that the Higgs field, the same quantum field responsible for giving particles mass, could be entangled with these structures, meaning wormholes might leave faint fingerprints in particle collider data. Yet the skeptics raise valid concerns. Renormalization, while powerful, feels like a mathematical band-aid, masking our ignorance of physics at the Planck scale. And if quantum wormholes exist, why haven't we spotted their effects in experiments? The answer might lie in their ephemeral nature. Like virtual particles, they'd borrow energy from the vacuum only long enough to flicker into existence before vanishing again, leaving no trace beyond subtle deviations in quantum probabilities. Future colliders or quantum gravity experiments might one day expose these ghosts, but for now, they remain tantalizing shadows in the math. What makes this theory so compelling isn't just its audacity, but its economy. It doesn't require exotic matter or cosmic strings, just the same quantum fields we already know exist, behaving in ways that push our understanding of reality to the brink. Whether these wormholes are real or not, they force us to ask, if spacetime itself is a quantum field, what other wonders might be hiding in its fluctuations? The answer could rewrite physics not with a bang, but with a whisper. Stephen Hawking's black hole information paradox is one of the most stubborn puzzles in theoretical physics. If black holes evaporate over time, what happens to all the information they've swallowed? Quantum mechanics insists information can never be destroyed, yet Hawking radiation seems to erase it completely. Wormholes might offer an elegant solution to this dilemma, not by letting information escape, but by secretly rerouting it elsewhere in the cosmos. Picture a black hole not as a dead-end trash compactor, but as a cosmic router encoding everything it consumes into spacetime itself, then transmitting that data through hidden tunnels to points unknown. The math behind this idea stems from an unexpected marriage between quantum entanglement and Einstein's equations. If two black holes become entangled, a scenario explored in the ER=EPR conjecture, they could be connected by a wormhole, forming a bridge where information isn't lost, just transferred. Imagine tossing a book into one black hole. Instead of being shredded into meaningless Hawking radiation, its information might stream through the wormhole's throat, emerging scrambled but intact in a distant region of spacetime. It's like burning a letter only to have its ashes reassemble in another mailbox light years away. This wouldn't just preserve information, it'd satisfy both quantum mechanics' demand for conservation and relativity's rules for black hole behavior. Critics argue that wormholes merely relocate the problem. If information exits through a wormhole, where does it go? Some models suggest it could emerge in a baby universe branching off from our own, a concept called black hole cosmology. Others propose it might be encoded on the inner walls of the wormhole itself, like data etched into a cosmic hard drive. The holographic principle adds another twist. Perhaps the wormhole isn't a tunnel at all, but a higher dimensional projection, with information painted on its boundary like a hologram. Each of these scenarios trades one mystery for another, but they share a tantalizing thread. Wormholes transform black holes from information shredders into cosmic archivists. Contrast this with the firewall paradox, which proposes a brutal alternative. As a black hole evaporates, its event horizon becomes a seething wall of energy that vaporizes any infalling information. Wormholes sidestep this violence entirely by offering a subtler escape route. Then there's black hole complementarity, which suggests information both burns at the horizon and radiates away intact, a quantum superposition that defies classical logic. Wormholes, by comparison, restore a kind of classical elegance, ensuring every bit of data has a one-way ticket to somewhere, even if we can't trace its path. The stakes here are cosmic. If wormholes resolve the paradox, they'd reveal a universe where nothing is ever truly lost, just hidden in spacetime's labyrinthine vaults. Future gravitational wave detectors or quantum gravity experiments might uncover clues like anomalous echoes in black hole merger signals that hint at wormhole throats vibrating beneath the chaos. Until then, the paradox remains a beacon, drawing us deeper into the quantum wilderness where relativity and entanglement collide, and where wormholes might just be the universe's way of keeping its secrets safe. When light passes a massive object like a galaxy or black hole, its path bends, an effect called gravitational lensing that warps distant starlight into ghostly arcs and rings. But what if that lens isn't a solid object at all, but a wormhole's invisible throat? Unlike the smooth distortion from a star or black hole, a wormhole's gravitational field would twist light in bizarre, telltale ways. Picture a flashlight beam passing through a curved glass bottle. The light doesn't just bend, It splits, warps, and reassembles in patterns no ordinary lens could produce. That's the smoking gun astronomers are hunting for, cosmic glitches where gravity's lens doesn't play by the rules. The math reveals why wormholes would stand out. A black hole's gravity bends light symmetrically like a perfect magnifying glass, but a traversable wormhole's throat, especially one propped open by exotic matter, would create a double lensing effect. Light skimming one side of the throat would bend inward, while light grazing the other side could get repelled, thanks to negative energies anti-gravity push. The result, twin or even quadruple images of the same background star or galaxy, arrayed in geometrically impossible configurations. Some models predict rings of light with dark central bands, like a halo with a shadowy gap where the wormhole's throat devours photons. Others suggest abrupt shifts in brightness as light flickers through the tunnel's turbulent edges. These aren't subtle effects, they're glaring anomalies shouting "wormhole here" to anyone who knows how to look. The hunt is already underway. Telescopes like Hubble and the James Webb Space Telescope have catalogued thousands of gravitational lenses, but a handful defy explanation. There's the case of HS 8104, a quasar whose quadruple images are arranged in a crosshatch pattern that defies conventional lensing models. Then there's the dark streak near the Andromeda Galaxy, a region where background starlight appears smeared as if brushed aside by an invisible vortex. While mainstream astronomy attributes these to overlapping dark matter halos or rare galaxy alignments, wormhole theorists see something more tantalizing: the fingerprints of spacetime's hidden plumbing. Future instruments could settle the debate. The Vera Rubin Observatory's legacy survey of space and time will map billions of galaxies, flagging lensing anomalies with unprecedented precision. Meanwhile, pulsar timing arrays, which monitor the clockwork beats of spinning neutron stars, might catch the fleeting warp of a wormhole drifting between Earth and a pulsar, subtly altering its rhythm. Even subtle distortions in the cosmic microwave background could betray ancient wormholes frozen into the universe's infancy, their lenses preserved like fossils in the afterglow of the Big Bang. Yet the challenge isn't just sensitivity, it's imagination. Astronomers are trained to filter out anomalies as noise, but finding wormholes means learning to embrace the outliers, the data points that don't fit. It's a reminder that the universe's greatest discoveries often begin as inconvenient glitches, hiding in plain sight until someone dares to ask, what if this isn't a mistake? What if it's a doorway? And that's the thrill of the hunt, not just mapping the cosmos as we know it, but decoding the places where it bends the rules. Time has always felt like a one-way river flowing inexorably from past to future. But wormholes might turn that current into a maze with no exit and no rules. Imagine a tunnel through space so twisted that it loops back on itself, not just bridging distances but stitching moments together. These are closed time-like curves, paths through spacetime where cause and effect become tangled, and the future could reach back to shake hands with the past. The equations of general relativity don't just allow for such paradoxes. They practically invite them, revealing a universe where time might be less a straight line and more a tangled ball of yarn. Take the famous grandfather paradox: travel back through a wormhole, prevent your grandfather from meeting your grandmother, and erase your own existence. Physics recoils at such contradictions, yet wormholes don't inherently forbid them. The key lies in their geometry. A wormhole with one end accelerated to near light speed, or parked near a black hole's crushing gravity, would experience severe time dilation. Return through it and you'd emerge in an era before you left. It's not magic, it's relativity pushed to its logical extreme. The universe, it seems, keeps a toolbox of temporal loopholes, and wormholes are the most notorious wrenches inside. But here's where quantum mechanics throws a wrench of its own. The Novikov self-consistency principle argues that the universe might enforce a kind of cosmic censorship, preventing true paradoxes. Any attempt to alter the past would simply fold events into a self-correcting loop. Picture trying to write a check that bounces. Your actions would adjust seamlessly to ensure the timeline's ledger always balances. In this view, wormholes don't break causality, they bend it into pretzels where every effect subtly predetermines its own cause. Skeptics, however, point to the chronology protection conjecture. Stephen Hawking's bet that nature abhors time travel as fiercely as it abhors a vacuum. Quantum fluctuations near a wormhole's throat might escalate into a lethal burst of radiation, collapsing the tunnel before any paradox can occur. It's as if space-time has an immune system, and time loops are the pathogens it ruthlessly eliminates. Yet even Hawking admitted this is more wishful thinking than proven law, a cosmic keep-off-the-grass sign with no enforcement mechanism, the wildest twist. Retrocausality, the idea that future events can influence the past. Quantum experiments already hint at this, with particles seemingly deciding their states retroactively based on later observations. Wormholes could amplify this effect, turning microscopic weirdness into macroscopic reality. Imagine a civilization sending messages backward through a wormhole, not to rewrite history but to ensure it unfolds as intended. The past becomes malleable not through force but through the subtle pressure of probabilities aligning across time. Debating these ideas isn't just academic, it's a referendum on reality's rulebook. If wormholes permit closed time-like curves, then time isn't a stage, it's a participant, shaped by the same forces that bend space. The universe might not care about our fragile notions of before and after, weaving a tapestry where every moment touches every other, and the only true constant is the endless dance of cause and effect. And that's a revelation more disorienting than any paradox. Wormholes aren't just science fiction, they're a playground for the boldest ideas in physics, stretching our understanding of reality to its breaking point. From Einstein's early equations hinting at cosmic bridges to the wild possibility of multiverse gateways, each theory we've explored reveals just how malleable the universe might truly be. Take the AR equals EPR conjecture, weaving quantum entanglement into the fabric of spacetime itself, or dark energy's potential role as a natural architect of wormholes. These aren't just abstract thought experiments, they're glimpses into a cosmos far stranger and more interconnected than we ever imagined. Consider the sheer audacity of these ideas. String theory paints wormholes as higher dimensional threads, while loop quantum gravity reimagines them as knots in spacetime's quantum fabric. Some theories suggest black holes might disguise secret tunnels, while others propose that collisions between neutron stars could birth fleeting wormholes in their wake. And then there's the holographic principle, where wormholes might not even be physical structures, but glitches in the universe's underlying code. Each perspective challenges us to rethink not just how we travel through space, but how we define it. Yet the most thrilling part isn't the answers, it's the questions that remain. Can exotic matter stabilize a wormhole, or is dark energy already doing the job? Do neutrinos shimmy through microscopic tunnels every second unnoticed? Could advanced civilizations be using wormholes right now, their highways hidden in plain sight? The beauty of these theories lies in their ability to spark wonder, proving that the universe's greatest mysteries are still up for grabs. So, which idea captured your imagination the most? Was it the mind-bending potential of time-traveling wormholes, or the eerie elegance of quantum entanglement as spacetime's hidden glue? Drop your thoughts in the comments, let's geek out over the possibilities together. And if you're hungry for more deep dives into the cosmos, hit subscribe. The universe is full of secrets, and we're just getting started.